right here, I could say that the direction is towards the back of the room. And all that is saying is that there's an area, there's the vector perpendicular to the surface is pointing towards the back of the room. So if I take an area vector, the magnitude is the actual area for a flat surface, length times width. And this is perpendicular to the surface. Now, this does present an issue of what is the orientation of this then? What's the direction of the area vector?
Because it could be up or down.
So, how do you resolve that? Well, they classify it in two types of ways. There's the open surface and the closed surface. And no bringing up Klein bottles. All right. In an open surface, I can get from one side to the other without actually passing through it. I can, if this is all I'm dealing with, I can get from this side to this side and I don't have to pass through the envelope. However, if I'm dealing with a sphere, or pretend it's a sphere, I cannot get from the outside to the inside without actually going through the surface. So for an open surface, there are actually two different directions. It's pick a direction. It's one way or the other. Typically, they set the direction equal to whatever's going to make, it's this is what you're calculating, but usually what makes it positive, but it doesn't have to be. Closed surface points outwards. The powers that be set down, they said for any closed surface, so for this right here, the area vector is pointing that way. It is not pointing towards the center of the ball. It's pointing away. We can get into a subtlety here. It points to the open air. If I have a surface that is strangely shaped, the area vector at this point points that way. That's still considered to be pointing outwards because it's not pointing into the surface, into the immediate surface. Area vector here is pointing that way. At this point, it's pointing that way. So what I have over here is, well, I have an electric field pointing that way. My area vector is also pointing in the same direction. So I'm going to take what I have over there, that the electric field is equal to electric field times the area is equal to Q over epsilon naught. Let's unpack it a little bit here. Notice this is a dot product. What's a dot product? Typically in 251, you first run across dot products in the work and energy chapter. You might potentially have dealt with it in kinematics, because one of the basic formulas, the Vf squared equals Vi squared plus 2a dot delta S. But what is a dot product?
Multiplication of vectors that gives you a scalar.
Okay, that's absolutely true. It is a scalar product. How do you multiply the vectors?
Straight across.
Matrices? With matrices?
No, the cross products you can do with matrices. I mean, you could finagle it with dot products, but I've not seen it. If that's a 60-degree angle, let's actually make it a 3, 4, 5 triangle. Make that 53 degrees-ish. What's the dot product?
It connects the 2 points of that, vectors.
Say it again?
It connects the ends of the vectors? Is that what we're going for?
Oh, no.
No.
No. Sounds like you're sort of morphing addition into that. What is multiplication if not some sort of complex addition? What are cross products? There are 2 types of multiplication with vectors. You got dot products and cross products. Dot products, scalars, as Gage said. Cross products? You would have dealt with them in torque. Okay. The 2 types of multiplication, one, you either you multiply parallel components or you multiply perpendicular components. With dot products, to produce the scalar, you end up multiplying parallel components. So the dot product between, if that's a force and a displacement, you're looking at the part of that 5 Newton vector that's in the same direction as the 4 meter vector, and that should be 3 newtons, and so it's 12 Newton meters or 12 joules. If you're dealing with a cross product, you're multiplying the perpendicular components, so that'd be 4 newtons, and so you'd end up with 16 Newton meters. You did a cross product. Dot product parallel. Which coincidentally is what we have right here. The electric field and my area vector are parallel to each other. That's why I got away with E dot A. I'm multiplying the parallel components, which in our case, done. This Q right here is the charge that's at the center of my sphere. Or more importantly, that Q right there is the charge that is within my Gaussian sphere. So that would be Q enclosed. Sometimes it'll just write N, but E and C for enclosed. It's the charge that's enclosed inside this Gaussian surface. We can take it one step further, because this assumes I got an electric field, the constant electric field and a constant area, that this is relatively simple to do, but what the heck? It's a calculus-based course. Let's throw some calculus into it. The dot is still there, is equal to the enclosed charge over epsilon sub naught. We have to do one other thing here, because our surface has to be a closed surface. And so we put a little circle right there to indicate we're integrating over an entire surface. An entire closed surface, I should say. If the surface is not enclosed, if it's not a closed surface, then there's no enclosed charge. This right here has a name. The symbol is a capital Phi with a little subscript E down here. It is a scalar because it is a dot product, as Gage was correct on that. And this is known as electric flux. Let's explore electric flux for a little bit. Suppose I have a bunch of arrows shooting from the wall to my right to the wall to the left, just going straight across. As I stick the envelope like that, those arrows are going to pierce it. Imagine this is wafer thin. If I turn it like this, how many arrows are going to pierce it?
A lot less.
So electric flux basically deals with how many arrows are going to be piercing the surface. Our arrows this time are electric field, the surface represented by the area. So we need to somehow deal with that. If my electric field's going this way, it's going to get the maximum piercing when the area vector is parallel or anti-parallel to the electric field. If it's anti-parallel, you'll end up with a negative number, not dealing with the closed surface right here, just electric flux in general. I guess that was misleading. Electric flux is the integral of E dot dA. Doesn't have to be a closed surface to define electric flux. This would be equal to the electric flux through a closed surface. So we define electric flux so that we get maximum value when the surface is being hit full on with the electric field, minimum when it's oriented differently, or from a math point of view, when the area vector is perpendicular to the electric field, you get minimum. When it's parallel or anti-parallel, you get maximum. If I gave you the area of this and the strength of the electric field and asked what's the maximum flux, this is what earlier I said you usually pick the direction that makes the answer positive. Yes, I could have an area vector going in that direction, in which case I have a negative flux. I could go in that direction to get a positive flux. Traditionally, you pick the direction that gets you the positive one, although the negative flux is not wrong. This, whether you like that form or that form, this is known as Gauss's law of electricity. At some point, early April, I believe, we'll have 4 of these type general laws. They're known as Maxwell's equations. This is the first of Maxwell's equations. Now you might be wondering, why are they called Maxwell's equations when the first one is Gauss's? Maxwell put in the last piece. He did not call them Maxwell's equations. Basically, I'm not quite sure where that started, but at some point they just started being called Maxwell's equations, and that sort of stuck. Maxwell actually didn't seem to have the ego that some physicists do. But Maxwell's contribution is that last piece made it possible to find out theoretically the speed of an electromagnetic wave. And that ushers in semi-modern physics, or semi-classical physics, in other words, relativity. But we're a couple months away from that. There's a more formal definition of this. This is just I took a very specific case, and I'm just going to make the claim it's generalized. So I have a surface here, three-dimensional surface. I've got a charge here of 5 coulombs, a charge here of -4 coulombs. And then if I ask what's the electric flux through the surface of this, well, what's the total enclosed charge?
1 coulomb.
So my electric flux through that surface, 1 coulomb divided by 8.85 times 10 to the -12 coulomb squared per Newton meter squared. we get a huge number there. Could somebody do that? I feel like there should be a number here when we start talking about units.
I got 1.13 times 10 to the 11th.
All right, and what units?
It'd be coulombs over Newton meter squared. So just one C.
Not coulombs over Newton meter squared?
Newton meter squared over Coulomb.
Yeah. And for some unknown reason, the physicists looked at that and said, yeah, we can deal with that. We're not gonna come up with one word. Or, we're not gonna honor anybody about this one, so you know what, we'll just live with it. Magnetic flux, they came up with a unit for it. Electric flux, no. Alright, so some of the stuff I just covered is chapter 24, some of it's chapter 25, I sort of blurred the two together. On Tuesday, I'll figure out what I missed. I'm sure there's some key things I missed from 24. One of the reasons I blurred them together is actually with Gauss's law of electricity, going through to find the electric field a certain distance away from an infinite sheet of charge, or from a line of uniform charge distribution, or from a sphere. We have another way of doing it, without going through all the calculus. It's not as much fun, but you get there a whole lot quicker. Unless, of course, you hate math, but then again, if you hated math, I don't think you'd be here. A love-hate relationship, I can see, but hating it, yeah. Have a wonderful evening. I hope that, I don't think we're gonna get much accumulation, but who knows, it could be snowing out there right now. Be safe. And if you're stuck at home again with your children, please don't murder your children. I like mine too, but that doesn't mean I wasn't ready to throttle them sometimes.